Good afternoon. I want to talk about data from the Brewer 171, the NASA Brewer. NASA, by the way, stands for National Aeronautics and Space Administration. Luftblick probably everybody knows. I want to thank my co-authors that have not made any comment on my presentation, so I didn't have to change anything. And I have to... The Brewer 171 is a double monochromator, an Mark III Brewer, and it has been deployed mostly at two stations in the northeast corner of Washington, D.C. at the Goddard Space Flight Center for about 10 years. And since 2010, it's in the center of Alaska in Fairbanks. And I will present data of this brewer plus data from OMI and from Aeronet. And I say here this is a quick overview of the measurements rather than an in-depth analysis. The reason is I'm not working with the brewer anymore, but I didn't want to come to this meeting empty-handed and decided that's a good opportunity to look at this long data series. And one of the co-authors will probably look into this more careful and then potentially publish something. This is the Ozone time series. In red is the data at Goddard, and in blue you can see we were for a short time in Fairbanks already in 2001, and since 2010 it's back in Fairbanks for political reasons. This is only direct sun measurements, and as a cloud filter I just used that the standard deviation is below 5 Dobson units and that the AOD at 320 nanometers is below 1.5. And this second part I think is very useful. If you have AOD measurements with your brewer, it seems to me that it does already the same removal than maybe visual methods or something else. That's just for direct sun. Another remarkable fact is that this is the original calibration of the brewer. There has been no change. All the lamp measurements indications simply showed that this brewer is solid as a rock. I think it's a brewer, if all of them would be like this, Tom would be very proud and Volodya would be very sad. But I'm glad that it is so stable. Here I show blue plots. The top one is for Goddard, the bottom one for Fairbanks, where I plot for every single ozone measurement the difference between this measurement and the average ozone of the same day. So if the ozone has a downward gradient or an upward, of course there are big differences here, but my point is that if you have a very long database, you can assume that on average the ozone doesn't have a daily an air mass factor dependence based on atmospheric reasons. So the red line in both curves is the median, and you can see how the median is very close to zero over in all these air mass factor bins that I have built. This is just a quick test. I have done it with other instrumentation, and if you have a stray light effect, the median goes down with air mass factor. And I'm a fan of calibrations of instruments that do not require any other instrument. So in principle, you could take a single brewer and make this plot and have a little bit an empirical stray light correction. You don't need any comparison, any formula, nothing. But I agree that the versions that were suggested the previous days are better. So the double brewer, as expected, has no stray light effect, no stray light error. And here you see two plots again, the left one for Goddard, the right one for Fairbanks. On the x-axis, the Brewer ozone column, on the y-axis, the OMI ozone column. And all I did here is the same filtering for the Brewer as described before. And I limited the OMI data to cloud fraction below 0.2, which basically means not much cloud in the OMI pixel. And you can see here that both of them have a slope of about 3% low, which means that OMI data are on average 3% smaller than Brewer data. Another thing that you can see is that days that I defined as significantly different between the two instruments, with the difference larger than 20 Dobson units, are much more frequent at Fairbanks than at Goddard. When you look at a few of these days, all the days where the difference between OMI and Goddard is above 20 Dobson units have a strong ozone gradient over the day. And so the conclusion is that OMI was probably simply sampling a different air mass than the ground data. So OMI pixel center is 29 or 84 kilometers different from the Brewer location, and was just looking at different air mass. There's no reason to believe that any of the instruments measured wrong. They just measured two different things. This is not true for Fairbanks, where we have some days with a strong gradient where we have a big difference. But we have quite a few days where OMI is strongly underestimating the ozone, and the people in Fairbanks will look a little bit into this. There might be some snow on the ground or another reason. Now this plot shows the same Brewer values, but now compared to OMI, now the difference between OMI and Brewer is a function of air mass. And it is not very strong, but there is definitely, also if you look at these red dots, air mass factor dependence. And by the way, the air mass factor, what I mean is just the optical mass. Some people call it 1 over secant theta, basically. Secant theta, 1 over cosine theta. And in both stations, the slope is basically the same, of about 2.2 to 3 Dobson units per air mass. So I was addressing this point at Goddard, and they say, that's the typical answer. In the next version, which is version 9, this should be better. I don't know why this comes. It could be a little stray light issue in OMI. And yeah. Now I looked at SO2. Now again, I took the original calibration the way it was given to us in 2000 when we got the Brewer. I apply a cloud filter, which is the same ozone cloud filter, but then in addition, I require that the standard deviation over the SO2 values is below 1.5. And I also filter and do not take this data where the SO2 is below minus 1.5 Dobson units, which are not so many. I mean, they are of course out of this plot, but it's not a big group. This last one doesn't take much away. And as blue again, Fairbanks, and red is Goddard. So we know that the SO2 is a measurement that is quite noisy in the Brewer, but the question is how accurate is it? So in this plot, I plot the slant column, the vertical column times the air mass factor for the Fairbanks values as a function of the air mass factor. And if you plot the median and make a linear regression, you have this slope of 0.76 Dobson units, which would mean that the average SO2 column in Fairbanks is 0.76 Dobson units, which contradicts everything that other measurements say that's by far much too high. So I could make a very reasonably bold move and say Fairbanks, the SO2 should be basically 0. So I can subtract the red line from the corresponding position on the red line from the blue data, and in this way kind of calibrate my data with a clear sky station or with an unpolluted station. If I do this, then the SO2 database looks like this, and the blue clouds of points are now forced to 0. So I basically said, look, Fairbanks cannot have a lot of NO2 or nothing. And still you can see how the Goddard data are significantly different from 0 and have somewhat of a downward slope. And in this next plot, I built daily daily averages of SO2. So the noise is not just, the noise in the SO2 measurements doesn't go away if you average 10 data. So even the daily averages are still pretty noisy. However, there's, with the assumption that the instrument is stable, which all the instrument indicators seem to suggest, you can really say that there's a downward slope in the SO2 of a certain amount. And you can even say that in these last years, this downward has stopped. It should, because this is nearly close to zero. And if you compare this to the Maryland, I just got this call yesterday, there's no image, EPA ground stations, in situ stations, they show a very similar behavior. So my point is that sometimes maybe we underestimate Brewer SO2. We can maybe use it much more than we think. Then aerosol optical depth. This is something which we calibrated at Goddard. So I guess Brewer doesn't come with AOD calibration, so it's calibrated in the lab. We took a lamp and calibrated. This is the time series of aerosol optical depth, again in Goddard and Fairbanks, at 320 nanometers. So it's this wavelength that is measured automatically when you do ozone measurements. You see this typical behavior with higher AOD in summer. And if you make a monthly distribution, you come to this image that shows, of course, in the urban place of Goddard Space Flight Center, much more aerosols than in Fairbanks. And even the cleanest days at Goddard, the 10% cleanest days are barely below 0.2 AOD. So I guess in Isanya, this is a polluted day down there, no? Anyway. On the left side is a comparison between the AOD at 320 nanometers and the AOD at 340 nanometers. So what we have been doing, we moved the slit mask in a so-called medium and high range. The medium range would be wavelengths between 327 and 343, and the high range between 347 and 363. So we have 3 times 6 wavelengths, 18 wavelengths for aerosol optical depth. And you can see that there's, of course, I think the laser may have disappeared. Oh, no, it's there. My eye has. There's a good relationship between AOD 320 and 340, but I just put a straight line there, but in reality, it's a more curvy difference between the two quantities. And this is a plot, is the difference between the Brewer AOD at 340 to the Aeronet AOD at 340 measured by CMEL. And also remarkable, there's hardly any difference between the two. Most of this scatter comes from a timing difference that Aeronet measures every 15 minutes, the Brewer sometimes measures in between, and you have a gradient of the AOD, and then your result is a difference that is simply because of the timing. And if I make this plot for different years, it always looks the same. So the Brewer, with the calibration of 2002, was completely stable for 10 years, giving the same AOD, while I know that the CMEL has been recalibrated every year. This is an example of what we also did with these 18 AOD measurements. So this is some day in the period which was exceptionally clear for Goddard, with aerosol optical depth between 0.1 and 0.25. And we have many days in the database with this low AOD, which have a very strong variation in the angstrom exponent. Here you see how in this 18 wavelengths, I just fit this exponential curve that gives me the angstrom exponent. And they vary a lot. And I think that's a very unique data set, because CMEL, as we know, has the smallest measurement at 340 and 380. And here, this is AOD of really high quality from 303 to 363. There are these rumors about funny behavior of the aerosols in these wavelengths. And with a Brewer, especially with a double monochromator, you can explore this. This is all the alpha, the angstrom exponents that we derived in the database as a function of AOD. And here the medians in different AOD bins, and the yellow line is a fit in the red dots. And as expected, the angstrom exponent decreases with higher AOD, since more aerosols or more aerosol optical depth usually means bigger aerosols and therefore smaller alpha. And I have looked at several of these negative data, negative alpha, the famous negative alpha. And the ones I looked at, I haven't looked at each single one, but they had all this situation where there was a gradient in the AOD, and the measurements in the low slit mask were measured at the time where the AOD was still lower. And then 5 minutes later, it was already higher, and 10 minutes later when we measured the higher ones. So I could all of them attribute to a strong change in the AOD that then when you plot them all, like in the previous one, in the same graph, gives you an apparent negative alpha, sorry, wrong direction. So the positive alphas look many of them look quite possible, but the negatives are all probably all outliers. Oh, not outliers, but caused by this time delay between the slit mask being in the low, medium, and high position. So my conclusions for the ozone time series are that including the AOD makes, for me, a perfect cloud filtering. I don't have to look at any plot. I don't have to, I'm not at a university where I can take students that look at images. And the Brewer is incredibly stable. That ozone from OMI is around 3% smaller than Brewer. Version 9 supposedly gives higher ozone, so for everybody who compares with OMI, and it agrees very well now, wait for version 9. And differences at Goddard are always explained by a strong gradient. Differences at Fairbanks cannot be explained always. And we have this air mass factor dependence of the difference between OMI and the Brewer. For SO2, my simple conclusion is this decrease of SO2 at Goddard is definitely real. The quantitative analysis is difficult because the Brewer has a bias and a factor. So in both cases, the B is usually positive and the F is positive. So I think Tom mentioned yesterday the SO2 algorithm and things like that could be explored a little more. And then for the AOD, using the Brewer for AOD, and maybe not just in AOD 320, seems to me a very useful addition to Brewer measurements. So I guess I repeat myself, but I don't know why, but the Brewer's 171 is extremely stable. I would think it's because they're only non-absorbing optical elements, quartz prism, quartz lenses, ground quartz diffuser, and then a photomultiplier in photon counting mode. But I guess there are other ones that have the same, built the same way and are not as stable. And so also because we modified the Brewer to make it polarization insensitive, we don't have to correct for any AOD measurements. You know? And this is a little bit a message of BK, but here my former branch head, who is a PI for, was the PI for Tom's and now is the science team leader for OMI, that the most useful data for climate pollution research and satellite validation come from long time series of uninterrupted, well-calibrated ground-based observations. That's not against aircraft measurements, but basically they suck up a lot of money and have little output. Here in this room, I guess I can say it. In another room, they would kill me. And this is why the operation and maintenance of networks such as the Brewer networks from Environment Canada, UBrewNet, NewBrew is so important and should be continued. Thank you.
My question is, what is the estimated uncertainty on the AOD measurement? And I was surprised to see very small uncertainties on the angstrom exponent. How do you estimate the uncertainty on the angstrom exponent?
Yeah, the uncertainty there is just the mathematical uncertainty. If you have assume that in principle they should be along this line, and you can calculate the RMS from each single one to this line. So it's more a mathematical. I wouldn't call it more noise than accuracy or something. The AOD measurement itself, the uncertainty is 0.01 accuracy. So very small.
Just a comment to the negative alpha values. I can confirm that I also found negative alpha in very extreme situations in the visible spectra, and I think that time I was able to avoid circumstances from technical circumstances, so that wasn't any failure in instruments or something like this. So maybe the negative alpha values are real in some situations. My supposition is that we cannot take the real value of the negative alpha too serious, but the negative alpha marks some very strong change in the size of the dominant size of the aerosol. So a big change, and when it means very large particles. So they are real. I think not perhaps not the value, but it marks a brutal effect.
That could be. Yeah. As I said, I didn't look at each single one. Yes. Yes. And right, this is cloud screened, and I often do not trust the Aeronet data, but this is from Goddard, so they have 50 units. So if they don't find a good result in these 50 units, they do something wrong. So I'm sure good Aeronet data. Yeah, I haven't looked in these details, but it is an interesting thing. And the people in Alaska now that is operating the brewer, they got a little bit motivation to look at this and hope. And they told me they have the snow cover and all this stuff. That is what I call the effective ground location, which is south or west, depending on the time of the day. Difference of this point minus the OMI pixel center. Like, yeah. So I took into account this. We had this at Sona a long time, that the brewer effectively always measures a little south of where he is, or she, it is. So such a person, so it's he. No, yeah, as I said, I used the original calibration. For the SO2, I'm sure the cross sections are off. I personally think they should just replace, or somebody who has time. The cross sections that I don't know what you say, Volodya, but the SO2 cross sections in the Brewer seem poor, yeah. And but ozone, you know, it's this chemistry cross sections that work perfectly, pretty good. No? Alberto talks more about cross section. Yeah, it was compared, and one way we were in sauna, 2008 or whatever, it was on top of the Spanish reference brewer. So I guess I just lucked out with this. No, all the indications. I mean, every day our schedule was at solar zenith angle, whatever, 115 in the morning, well before sunrise. We did all these lamp tests. I mean, we used 3H standard lamps over the time. And sure, then you have a change in standard lamp that is a different, but whenever we had the same standard lamp and neutral density filter, everything we checked, it's very stable. So that was the reason. And of course, the comparison with the Spanish one, which and the aerosol, I mean, the AOD comparison is much tougher than the ozone. Ozone is much more forgiving. But if you had AOD 340, measure for 10 years, and you compare to Aeronet, which is, the Goddard Aeronet is the reference Aeronet instrument, and it's the same, then that's a very good indication.
I agree, but will be accepted when you have a comparison with a reference, because it's the only chance to have to be sure. So we we compare with other instruments. We say, okay, you are inside 0.5% of our instrument, so you don't have to change the calibration.
I'm not in charge anymore. You have to ask the Alaskans. So.